Whenever you're trying to make a decision, it is likely that at least part of that decision will be based on some kind of measurement. How fast is the line running? How much do we make today? How many customers did we serve? How well did we serve them? What's causing that problem? Do we even have a problem in the first place? If you can't trust the measurements used to answer questions like these, you're not going to make good decisions. In my experience, there's a lot of wasted time, effort, and patience due to measurement systems that simply cannot give you the information you need. But people don't know that since measurement systems themselves are rarely tested. In my new online course, Measurement System Analysis for Continuous Data, we will do a deep dive on how to properly conduct studies to determine if you can trust the numbers you need to make important decisions, and then how to determine if a gauge is acceptable for the use you have for it. And along the way, I'll let you in on some tips, tricks, and secrets that will give you a big advantage of doing MSAs. Let's get started with a story and some common reasons people think they don't need to do MSAs. I went to the Colorado School of Mines for my undergrad degree in metallurgical materials engineering. While we did a lot of labs, we were never taught to be skeptical of the things we used to make all those measurements. The instructions told us to measure out 10.50 grams of some substance. We never tested to see if the balance we used for that was right or consistent. Maybe that's part of why we used to call chemistry lab casino lab. I don't know, maybe it was just me. Anyway, it never crossed my mind that these instruments themselves might not be giving me the right values. They were in a science lab. They were made in Switzerland. They were very expensive. It wasn't until I was working at an aluminum company that I first realized that the numbers we got from a measurement system might not be so infallible. We were concerned with how much residual stress was in a piece of aluminum. If there was a lot of stress, it would change shape after you machined it. To test this property, we would take a sample of the aluminum, use a bandsaw to cut it down the center of the thickness, and measure how much the ends opened or closed. The reasoning was that if there was a lot of stress, the sides would open up more. Of course, we called it the tuning fork test. We would scrap huge plates of metal based on this test. Then I took a class in experimental design, and that happened right at the time the company was looking for ways to reduce residual stress since customers were complaining about it. Being new to experimental design at the time, I followed the steps religiously. One of the first steps was to verify that whatever measurement system you're going to use was stable and was actually related to the underlying property that you were trying to study. The first thing we found was that the test had never been shown to be predictive of how the product performed after machining. So we potentially had a measurement system that didn't relate to the customer's experience. That was pretty bad, but we figured we could do the experiment and then use the metal produced as an opportunity to see how the tuning fork measurements related to their experience in machining our metal. But first we needed to determine if the measurement system was stable through time and to quantify its variation when measuring the same specimen. To do that, I did what I'll call a short-term gauge study. We took some samples, diced them up, and tested them. The findings shocked us. At best, the tuning fork test was a random number generator. Measurements on samples from the same plate would result in radically different results on the test, sometimes even negative numbers when the ends bowed in. The implications sunk in. We had scrapped millions of dollars worth of aluminum for years using a test that had never shown an ability to predict customer experience and couldn't even get close to the same number with repeated measures on the same piece of metal. So we went back to the drawing board, literally, and designed a new way to measure residual stress that eventually did pass an MSA. Since that time, I've been very skeptical of untested measurement systems, and almost universally have found that the measurement systems themselves do not give results to the level that the people using them needed. Often, difficult problems people have been working on for years are actually just bogus measurements, and there was no problem there at all. The first tip here is don't trust any gauge that hasn't been tested. When I tell people this, they often say that their measurement system must be okay, since it has an up-to-date calibration sticker and the spec sheet the salesperson gave them says that it's capable of astounding precision. A calibration sticker just shows that your measurement system at some point was compared to a standard and adjusted until it agreed with it at some level of precision. There are several problems with just depending on calibration to tell you if a gauge is working. The first is that it's only a snapshot in time. I was at one company that calibrated micrometers every 3 months. At the final inspection, they used these micrometers to measure the thickness of the product and determine if it met spec. At one of these calibration events, an employee's micrometer was way off standard. It turns out that the employee dropped the micrometer at some point and was scared to tell anyone. That meant that at some point in those 3 months, some bad product had passed as meeting spec, and some good product had been scrapped. We had to go back to our customers to let them know we could not guarantee the thickness was to spec on potentially 3 months of shipped product, not sure exactly when. They were not too happy about that, since most of the product had already been incorporated into finished product. The next problem is that calibration is based on measuring some standard, like a gauge block or shims, that is traceable to a national standard. Unless you're making these standards, this might have nothing to do with what you're actually trying to measure in your process. I recently heard of a measurement device that was shown to be completely incapable of measuring the items produced by the user, not to mention very far off of what the marketing literature claimed. This was shown to the device's manufacturer, and the user said they wanted a refund. The manufacturer denied the claim, saying that they were, quote, using it wrong, and that it measured standards perfectly in line with what they claimed in the brochure. The fact that it couldn't be used to measure what they bought it for was irrelevant. And another problem is that calibration typically doesn't track the measurement device through time. I was involved in another ongoing issue that a lot of people were working to fix. They were trying to control the composition of a product. It was very expensive to manufacture, but they kept having to remake lot after lot because what seemed to be the same recipe resulted in both in and out of spec material. When they finally performed a measurement system analysis, they found out that the device used to measure the composition drifted through the week, so a product that was perfectly in spec would fail if it was made at the end of the week. This was years of wasted effort and capital expenditures to try to fix a problem that wasn't even real. Finally, calibration itself can be the source of a problem. Another process had an ongoing problem of putting too much or too little of the coating on the product. So once a week, a very methodical maintenance person would go to calibrate the radiation gauge that measured the thickness of the coating. He would put in various thicknesses of samples and turn a knob until the machine read exactly the thickness marked on the different samples. The problem was that he was adjusting based on the common noise of the gauge itself. So what he was really doing was shifting the average reading up and down every week. Since this measurement system was part of the control loop that adjusted air knives to set the thickness, the actual thickness of the coating went up and down every week as well, and as a consequence, the total product variability was high. As an experiment, I had them stop the weekly calibration. The thickness variability was cut in half as a result. The problem was entirely the result of too frequent calibration. Your second tip is calibration is necessary but not sufficient to determine if a gauge is useful to you. Of course, I'm not the first one to be stung by bad measurement systems. For quite some time now, people across many industries have performed what are called Gauge R&R studies. Notably, the auto industry in the US has published a handbook called Measurement System Analysis and shows an example gauge study. Now, there's nothing wrong with that example. We will refer to that as a potential study, but it's wholly insufficient by itself to determine if a measurement system can get you what you need. The problem is that this is often the only study ever done on a measurement system, and it doesn't tell you what you need to decide if you can use it in a real process. These Gauge R&Rs typically measure 10 parts 3 times across one or more appraiser. They're designed to give you a quick and dirty assessment of how much variation you get when you remeasure the same sample and then between appraisers. What this type of Gauge R&R does not assess is through time stability of the gauge, and with its limited number of samples and few repeated measures, its estimate for measurement error not particularly precise. That means that drifts through the week or dropping a micrometer will go undetected until it is too late, if ever. Although the MSA handbook itself warns against this, many companies use the calculated % R&R number as an acceptability measure. It simply cannot be used that way. You might have a measurement system with a high % R&R that's still acceptable to be used in your process, or a low one that is not acceptable. We will talk in the course about creating and testing criteria for acceptance. Your third tip is Gauge R&R by itself is not sufficient to determine if the measurement system is useful to you. If you use measurements to help you make decisions, you need to know that you can trust these measurements. Join me exploring how to properly perform measurement system analyses for continuous data in my new online course. You might just end up saving yourself a lot of time, money, and a little slice of sanity.